All right, let's jump right into it. Today in this explainer, we are decoding exactly how the universe moves and changes by looking at the true language of dynamic systems. We're talking about partial differential equations, or PDEs. I want you to picture something for a second. Imagine a massive wave crashing against a shore. Or picture yourself holding a metal rod near a fire, feeling the heat slowly inching its way up the metal toward your hand. How do we literally write that down in math? The universe doesn't just change in one simple, neat little straight line, right? Things are changing across distance and time all at once. To capture that multidimensional reality, we absolutely have to have a specific mathematical framework. So here is our game plan for today. We'll start with real-world dynamic phenomena, figure out what a PDE actually is, break down their anatomy, order, and degree, look at modeling the world with some popular equations, and finally, wrap up with forming PDEs using elimination methods. Okay, starting right off with Section 1, Real-World Dynamic Phenomena. You know, the really cool thing here is that these aren't just like abstract numbers floating in a textbook somewhere. They are the essential language of dynamic systems. Whenever something is in motion and being pushed and pulled by multiple factors at once, PDEs step in to help us predict exactly what's going to happen next. Whether we're dealing with physical, biological, or economic systems, they are the absolute go-to tools scientists use to translate behavior into pure mathematics. Formally speaking, a partial differential equation involves multivariable functions and their partial derivatives. Basically, what that means is it lets us track changes across multiple dimensions at the exact same time. Think about temperature. How it changes over time is one dimension, but how it changes over time and across the physical length of a metal rod, now you've got multiple independent variables. And honestly, that is exactly where the PDE shines. Just think about the sheer scale of where this stuff is applied. Over in physics, we're using them for sound waves, fluid dynamics, and heat distribution. In engineering, they are absolutely critical for analyzing the structural integrity of skyscrapers, mapping electromagnetics, and running things like the finite element method. And it definitely doesn't stop at hard science. Biologists and economists use PDEs to model complex population growth or economic variables that are shifting over both time and geographical space. They're even the secret mathematical sauce used to animate hyper-realistic water and smoke in your favorite video games. Moving right along to Section 2. What is a PDE? Let's clear something up. An ordinary differential equation, or ODE, basically deals with a single independent variable. It's kind of like tracking one single car moving in a one-way lane of traffic. But a PDE? A PDE handles multiple independent variables. It's mapping the total chaos of a massive multi-lane intersection where everything is changing simultaneously. Our dependent variable relies on both x and y, perfectly capturing that whole multi-dimensional movement. All right, Section 3, Anatomy, Order, and Degree. Just like classifying an animal in biology, we classify PDEs by their order and degree. Why? Because it tells us exactly how complex they're going to be to solve. The order simply points out the highest derivative present in the equation, so are we looking at a first or a second derivative? The degree, on the other hand, is the highest power, or exponent, of that specific highest derivative. Oh, and if an equation keeps things simple, only containing the first degree of its independent variables and partial derivatives, we call that a linear PDE. Now, if we wrote out the full partial derivative symbol every single time, our math would quickly turn into giant, unreadable walls of text. No one wants that. To prevent it, mathematicians use this really elegant shorthand notation. P stands for the partial derivative of z with respect to x, q is with respect to y, r is the second partial derivative with respect to x, s is the mixed second derivative for x and y, and t is the second partial derivative with respect to y. Honestly, memorize these. It is a beautifully efficient code, and you'll see it everywhere. Let's check out Section 4, Modeling the World with Popular Equations. First up is the one-dimensional wave equation. By relating the second partial derivative with respect to time directly to the second partial derivative with respect to space, we can mathematically model the vibration of a plucked guitar string, or even a radio wave traveling through space. It's pretty amazing. Next, we have the one-dimensional heat conduction equation. Notice the slight mathematical tweak here. The time derivative is only first order, while the spatial derivative stays second order. This perfectly predicts how heat flows through a solid object. Remember that metal rod heating up we talked about earlier? This is the exact math behind it. Taking it up a notch into two dimensions, we run into the Laplace equation. Here, the sum of these second partial derivatives with respect to x and y equals 0. This equation is an absolute cornerstone in physics. It perfectly describes a steady-state system like steady-state heat conduction or smooth fluid flow, where the system has reached total equilibrium and absolutely nothing is changing over time. Building directly on Laplace, we get the Poisson equation. Now, instead of equaling 0, it incorporates a source function on the right side. Basically, this lets us model systems that are driven by an internal source, like a distribution of electric charge or a massive gravitational pull. Finally, Section 5, forming PDEs using elimination methods. So we've seen the final equations, but how do we actually construct them from a known function? Well, think of it like a giant puzzle. Our main goal is to kick arbitrary constants out and replace them with our partial derivatives. We systematically differentiate with respect to x, then y, and then both. By isolating those constants, we can cleanly substitute our shorthand back in. And boom, you get a pure PDE without any of the original arbitrary constants cluttering things up. Now, what if we're eliminating whole arbitrary functions instead of just constants? Actually, it's pretty straightforward. We use the chain rule to differentiate, which spits out a system of equations. From there, setting up a matrix and taking its determinant gracefully guides us right to a final differential equation in the classic format. Lowercase p times capital P plus lowercase q times capital Q equals r. Let's look at a super quick example to make this concrete. If z equals an arbitrary function of 2x plus y, substituting our variables collapses all that complexity. By finding our derivatives p and q, we immediately see that p is exactly twice as big as q. The arbitrary function literally just vanishes, and it leaves us with a neat, highly solvable PDE. 2q minus p equals 0. We've gone all the way from the crashing waves and heating metals of the physical world, right down to the precise matrices and shorthand notation that allow us to capture them on paper. You now have the foundational tools to translate our incredibly dynamic, multivariable universe into solvable mathematics. The language is entirely yours. So, what chaotic, real-world system are you going to decode first?